Lithium-ion thermal runaway creates simultaneous threats: fire, toxic gas, flammable atmosphere that overwhelm manual response unless detected and suppressed within initial seconds. Your laptop battery contains enough chemical energy to kill everyone in the module, and disconnecting the power cord won't stop what's already started. The alarm sounds at 8:47 station time, and the acrid smell reaches your nose before you identify the source. Your ThinkPad was running experiment data analysis, routine work, nothing unusual. Now smoke wisps from the keyboard. You reach for the power cable, yank it free. The laptop keeps heating. This isn't an electrical fire you can interrupt by cutting power. Inside the battery pack, one cell has reached 250 degrees Celsius from an internal short circuit, damage from a drop last week, or a manufacturing defect that waited 18 months to matter. The electrolyte has begun decomposing exothermically, releasing heat that makes the reaction accelerate. You've just triggered a chemical cascade that feeds on itself. The cell ruptures. Gas vents, hydrogen, methane, ethylene mixed with carbon monoxide and hydrogen fluoride. You smell burning plastic and something sharper, chemical, wrong. The adjacent cell absorbs the heat. Its temperature climbs past 200 degrees Celsius. 15 seconds later, it ruptures. The cascade has started. Your 6-cell laptop battery will propagate through all cells in under 2 minutes, releasing more than 3 liters of flammable, poisonous atmosphere into a module with 80 cubic meters of air. Do the math. That's a 3.75% contamination before dispersion, and the ventilation system is about to distribute it everywhere. The alarm sounds at 8:47:23, detecting particulate concentration above 150 micrograms per cubic meter. Gas sensors, designed to detect thermal runaway precursors like volatile organic compounds from electrolyte decomposition, registered anomalies 8 seconds before visible smoke appeared. Response time matters when propagation spreads at 0.5 to 5 centimeters per second through a battery pack. Cell spacing in your laptop is 3 millimeters. The thermal front bridges that gap in under 6 seconds once the first cell vents. Detection buys you seconds, not minutes, and those seconds determine whether you contain the fire or become a casualty statistic. Carbon monoxide at 1600 ppm causes unconsciousness in 20 minutes and death in 2 hours. You're currently breathing air climbing toward 800 ppm and rising fast. Hydrogen fluoride causes respiratory damage at 30 ppm. Tests have measured over 200 ppm during battery venting. The gas is corrosive to lung tissue, and exposure creates systemic toxicity that kills hours after you think you've survived. Your station carries no antidote because the treatment requires immediate calcium gluconate administration and controlled ventilation, neither of which exists in orbit. Prevention is the only medicine that works here. You grab the thermal runaway containment bag, silver fire-resistant fabric, stored in the emergency equipment locker you hoped would gather dust forever. 40 seconds have elapsed since the first cell ruptured. The laptop is hot enough to blister skin, smoke pouring from the vents. You don gloves, open the bag, position it. The laptop goes in. Seal the bag. The fabric contains heat up to 900 degrees Celsius and absorbs the force of cell ruptures. Flames inside the bag aren't your problem now. Containment is. But the module air is already contaminated. Your crewmate seals the hatch to the adjacent module. You're isolated now. 2 crew in 80 cubic meters with a chemical bomb contained but still reacting. The environmental control and life support system wasn't designed to scrub battery fire byproducts. It handles metabolic carbon dioxide, humidity, trace contaminants from human bodies, not the complex cocktail of metallic compounds, volatile organics, and toxic gases from lithium-ion thermal runaway. The filtration system can't save you. You need to vent. The decision takes 5 seconds. You initiate controlled atmosphere venting to space. Station protocols permit this for contamination events when crew can isolate to unaffected modules. Air rushes out through the vent valve, carrying carbon monoxide and hydrogen fluoride with it. Pressure drops. Your ears pop. The flow rate is controlled. You're not explosive decompressing, just exchanging poisoned atmosphere for vacuum, then refilling from oxygen reserves. 15 minutes to complete the vent cycle. You monitor carbon monoxide sensors, 800 ppm, 650 ppm, 420 ppm, 180 ppm. Breathable again, barely. Inside the containment bag, thermal runaway propagation continues through cells 4, 5, and 6. Peak temperatures exceed 779 degrees Celsius as each cell's cathode decomposes, releasing approximately 800 kilojoules per kilogram. The bag's polymer gel absorbs thermal energy. Heating rate during violent runaway reaches 15 degrees Celsius per minute or higher without intervention. Time interval between cell failures varies, 7 minutes maximum under ideal cooling conditions, but your laptop cells are packed tight with minimal thermal barriers. Actual propagation takes 90 seconds total. The bag prevents that heat from igniting surrounding materials and channels vented gases into its sealed interior instead of your breathing space. Post-incident analysis reveals what nearly killed you. The laptop battery, manufactured 18 months ago, subjected to 247 charge cycles, dropped once during equipment transfer, experienced separator failure in cell 3. Microscopic dendrite growth bridged anode and cathode, creating a low-resistance path that generated heat faster than the battery management system could detect and respond. By the time temperature sensors registered an anomaly, the cell had already entered self-sustaining decomposition at 250 degrees Celsius. Physics doesn't wait for electronic safeguards to catch up. Historical precedents underscore what you just survived. In 2009, NASA tested a lithium-ion battery that overheated, caught fire, and detonated inside an enclosed steel locker. Controlled test environment, trained observers, fire suppression equipment standing by, and the energy release still exceeded predictions. In 2022, the cargo ship Felicity Ace burned for weeks in the Atlantic Ocean, carrying 4,000 vehicles, including electric cars with lithium-ion battery packs. Firefighting crews couldn't extinguish the cascading thermal runaway. The ship sank. On Earth in Jamaica, New York, a warehouse fire involving 200,000 lithium batteries created a chain reaction that halted rail service for 10 hours. Firefighters deployed 1,000 pounds of Purple K dry chemical. It didn't work. They buried the burning batteries under 3 feet of cement. You can't do that in orbit. The containment bag prevented catastrophe. Without it, 6 cells venting into open air would have generated peak temperatures exceeding 1,100 degrees Celsius in the immediate vicinity. Burning electrolyte would have ignited nearby materials, documentation, fabric equipment covers, plastic cable insulation. Instead of a contained battery fire, you'd have faced a spreading combustion event filling the station with particulates and combustion byproducts. Metallic compounds from battery electrodes would have coated every surface, contaminating equipment and creating long-term health hazards from inhalation. The bag's fire-resistant construction turned potential disaster into manageable incident. But here's the irony that keeps you awake during the next sleep cycle. The station carries 184 lithium-ion batteries across laptops, tablets, cameras, power tools, and experiment equipment. Each one is a statistical risk. Aviation recorded 322 lithium battery fire events between 2006 and 2021. Aircraft can land, you can't. Energy density makes lithium-ion batteries useful, 100 to 265 watt-hours per kilogram, more than any alternative chemistry at acceptable mass. That same energy density makes thermal runaway catastrophic. The chemical potential that runs your laptop for 8 hours releases as heat and toxic gas in under 3 minutes when containment fails. Mars missions will carry more batteries, not fewer. No resupply option means more spares, more redundancy, more devices, more cells, more thermal runaway probability accumulating over 900-day missions. Solid-state batteries using ceramic electrolyte might eliminate the flammable liquid decomposition problem, but they're experimental, cost 5 to 10 times more, and deliver lower energy density than current lithium-ion cells. Lithium polymer with improved thermal management offers incremental safety improvements, but doesn't eliminate the fundamental chemistry that makes cells vent at 250 degrees Celsius. Advanced detection systems using gas composition sensors and temperature rate of change monitoring can trigger alarms within 500 milliseconds of thermal anomaly detection. Early warning extends your response window from seconds to slightly more seconds, still not enough to prevent runaway once dendrite growth shorts the cell internally. The laptop that nearly killed your crew sits in the containment bag, vented to space during the next EVA, and photographed for the incident report. 6 cells, 47 watt-hours total capacity, 63% weight loss from thermal runaway. The manufacturer will analyze the failure mode. Procedures will be updated. Battery inspection intervals might be shortened. Detection sensitivity will be recalibrated. None of this changes the underlying truth. You depend on portable electronics. Electronics depend on lithium-ion chemistry, and lithium-ion chemistry has failure modes that generate more heat and toxic gas than your environment can tolerate. Dependency creates vulnerability. Every battery aboard represents accumulated risk that compounds with mission duration. The same energy density that makes orbital operations possible, running experiments, analyzing data, documenting research, communicating with Earth, makes fire containment necessary. You can't eliminate the batteries without eliminating the capability they provide. You can't eliminate the risk without eliminating the chemistry. Physics doesn't negotiate, and the equation balances with your life as the variable that adjusts.